Hello everyone, welcome to our session today. In this video, we're going to explore a fundamental topic in data structures called the linked list data structure. But before we delve into the nitty-gritty of a linked list data structure, let's first understand what they are. A linked list is also a collection of elements, same as array data structure, but linked list is a dynamic data structure, meaning that the size of the linked list can grow or shrink at the runtime. That is not the case with an array data structure. We learned that arrays are fixed size and they're also called the static data structure, while linked lists are dynamic data structure. Also, unlike array elements, a linked list element, instead of being stored in contiguous blocks of memory, they are stored in non-contiguous blocks of memory. Basically, a linked list is comprised of individual elements, also known as nodes. So in the array data structure discussion, we learned about memory representation of an array data structure. We saw how elements are stored one after another in contiguous blocks of memory. So when we declare an array, blocks of memory are allocated, and the memory manager will allocate a memory address to the first element of the array. Say memory manager allocated address 100 to the first element of the array, and if I want to store integer values, say 1 2 3 4 5 6 and so on. So since the elements are stored in contiguous blocks of memory and each element takes 4 bytes of memory location, the next item will have an address of 104 and the next item will have an address of 108. But this is not the case with a linked list. As I said, linked list is comprised or made up of objects called nodes. In each node we store data elements, and each node, when we create a new node, each node is created in a random location, not contiguous location like arrays. So each node is basically made up of two parts, having the data part for storing information and also a link or a pointer part, link, or let's call it pointer, for pointing to the next node. So say if I want to store number 5 in this node, so the memory manager say created this node at a location say 500, but if I want to add more data item to my linked list, I can create a new node having same data part and a link part. So in data part I can store number 7, and in the link part, so I store initially null is pointing to nothing. So to this also initially will have a null pointing to nothing. Say the memory manager created this new node at location 900. To create a link or connect these two links, what I can do is I can store the address or the memory address of the newly created node to the link part or the pointer part of the previously created node. So instead of null here, I can store 900. So once I store 900, a link between these two nodes will be created, so I can keep track of the nodes. Say I want to store another number in my linked list data structure. What I can do, first I'm going to create a new node. So the memory manager is going to create this newly node in a random or non-contiguous location. Say this node is created at location 115. So I can store my data in the data part of this node. Say I want to store number 70 here, and initially the link part or pointer part of this new node is going to be null, is pointing to nothing. To create a link between this the previous node and the newly created node, what I can do is I will store the memory address of the newly created node at the pointer portion of the previous node. So I can store number 115 or memory address 115 here, so a link is created between these two nodes. In the case of arrays, calculating memory addresses of subsequent elements is straightforward, because we can leverage the base case address, the base address or the base address of the base element, given that elements are stored in contiguous blocks of memory. We saw how to, also we have the concept of indexes in array data structure. So the first element has an index of 0, second has an index of 1 2 3 and so on. So using the base address or the address of the first element, we can calculate the address of any elements we want using their index values. But this is not the case with a linked list data structure where elements are not stored in contiguous blocks of memory. As I said, to maintain the structure of a linked list, we need to store additional information. Each element or node in a linked list must hold the memory address of the next node. In this case, we can see the first element store a memory address of the second element, which is 900, and the second element store the memory address of the third element, which is 115, and the third element stores the memory address of nothing, or the linked part points to null, meaning that it is the end of the linked list. The necessity for storing the memory address of the next node or newly created node in the linked part of the current node is due to the non-contiguous nature of linked list storage, which requires this pointer to connect and track and keep track of all elements or nodes within a linked list. So in the case of array data structure, when I define an array, say int array, I want to call it ARR. In this case, we know the type of each element stored in this collection or in this data structure, and also we know the size of each element. So in this case, when I define integer, we know the type of each element is going to be integer, and also the size of each element is going to be 4 bytes, since integer takes 4 bytes of memory location. But what about the type and size of each node in a linked list data structure? So what is the type of this element and what is the size of this element? To answer this question, let's first understand how we can create a node. So we can create a node either using a struct or a class. So to create a node, I can use a struct, then I can give a name to my node. Say I want to call it node. And inside the brackets, I have data parts. Say I want to store integer values, call it data. And this node or each node is going to have a pointer to the next node that's going to be of type node pointer, and let's go call it next. So this way we can define a node, or we can use class to define a node. So say I want to call it public class. Say I want to call it node again, and inside this class, say I want to store integer values and data, and this class or this node is going to have a pointer to the next node. The pointer is going to be of type node, since it is going to store an address or memory address of object type node, and let's call it next. So this way we can define a node. So to determine the type of this node, this is a complex or user defined type. So the type of each node or each element in a linked list is going to be node. Node is a complex data type or a user defined data type. In this part, we can store as many data as we want. We can store primitive data types here. We can store non-primitive data types here. We can store a linked list, another linked list here. Say I want to store beside an integer value, I can store a string value also in each node, string names, for example. So this way the size of each node depends on the declaration of the node. So in this case, the size of a string plus size of int data plus size of this pointer is going to comprise this total size of this node, and also the type is a user defined type. So now let's understand what a pointer is. When I say node next is a pointer to the next node, what I mean by a pointer is a variable that holds the memory address of another variable. In the context of programming and data structure, pointers are used to refer or point to another data element in memory location. In linked list, pointers are particularly important. A linked list is a linear data structure in which elements are separate objects called as node. As I just mentioned, each node contains two fields, the data and the pointer to the next node. The data field stores the value or information, while the pointer field holds the address of the next node. When you want to access the next element in a linked list, you can use the current node's pointer to get the next node. So what I mean by pointer, say I have an object called student here. This class or object has int id, name, or age. This is a construct, the default constructor, and this is a overloaded constructor, and also I have some fields here. To make a pointer to this object, what I can do is I can create a variable of the type object. In this case, I can create a variable of student, type student, and call it let's s1 equal to new student. So the new keyword is going to create an object of type student in the memory location. An object will be created. Say this is an object student, student, and sorry, student, and we saw a student has int id, age, and name, a string name. So when we say int student s1 equal to new student, so new keyword is going to create an object at a random memory location, say 5000. So the variable s1 is going to point to this memory address. Okay, that's why this variable s1 is called a pointer to object. So this new keyword creates an object of type student, and this s1 is pointing to this object. So when I create another variable of this type of student, say I want to call student s2 equal to s1. So in this case, I have created a new pointer to the object s1. In fact, s1 and s2 are two variables that are pointing to the same memory location. So when I created s2 is also pointing to the same memory location. Since I haven't used the new keyword, so s2 is not a new object. They are the same object pointing. There are two different variables pointing to the same object. So same way, when we want to access the next element in a linked list, we can use the current node's pointer, to point to the next node and access the element in the chain of the data items. So the pointers are essentially tells you where to find the next piece of data in the memory location. When traversing a linked list, we will start at the head. The first element is called the head element and follow the pointers going all the way until we reach null pointer, or indicating the end of the list. So in a nutshell, a pointer is a reference to a location in a memory. In case of linked list, a pointer is a reference to another node that is stored somewhere in memory. So this pointer is pointing to this node, which is stored in a random location in memory. So this is one of the drawbacks of linked list data structure, that besides storing the information or data, we need to store additional information called the pointers to the next node. This makes a linked list data structure require more memory in compared to an array data structure. You might ask, what is the size of a pointer in a node that makes linked list require more memory or resource than an array data structure? Well, to answer this question, the size of a pointer in a linked list, or any context for that matters, depends on the architecture of the system on which your program is running. In a typical 32-bit system, a pointer typically takes 4 bytes of memory location or 32 bits of memory location, while in a 64-bit system, a pointer generally takes 8 bytes of memory location or 64 bits of memory location. However, this can vary depending on the specific programming language, compiler, or system you're using. For example, some high-level languages abstract away the exact size of pointer to make programming easier, and the underlying principle applies. As the linked list name suggests, a linked list is a list of data items or nodes that are connected to each other, forming a chain of data or a chain of nodes. In this case, we can see we connected different nodes using the pointers, forming a chain of data items. So in a linked list, usually the first element or the first node is called the head node, and the last element in the linked list called the tail node. So the node pointing to null or pointing to nowhere indicates the last element of the linked list. So the head pointer stores the address of the first node in the list using the head pointer. We can traverse over the linked list to access the next element using their pointers. Unlike arrays, as I mentioned, in linked list, random access is not possible. This is the drawback of linked list because data is not stored in contiguous blocks of memory. They are stored in scattered locations in memory. Only sequential access is possible in linked list, not random access like arrays. So this is one of the drawbacks of linked list. Using the head pointer, we can start traversing, and using the each node's link part or pointer part, we can access the next node. So this traversal or access of each element, in worst case, the time complexity takes a linear time or big O of n. Now you might be wondering why when we already have arrays, why do we need another data structure like linked list? Well, arrays and linked list, while similar in some ways, they both store collection of items. They have distinct advantages and disadvantages over each other, making them suited for certain tasks than other. Now let's explore what the advantages and disadvantages we encounter with array data structures. So with array, they are great for tasks that require random access. This means you can directly access any elements at any index in constant time, or big O of 1, which is very fast. Furthermore, arrays have less memory overhead because they only need to store the data, and there is no need for extra space for the pointers like linked list data structure. Some of you might ask, what is overhead and what do you mean by memory overhead? In the computing or the field of computer science, overhead usually refers to the additional resource or work required to perform a certain task beyond the resource used directly for the task itself. In the context of data structure like linked list and array, the term memory overhead is used to indicate the extra memory used by the data structure beyond what is necessary for storing the actual data. For example, in a linked list, each node contains a data and also a pointer or a reference to the next node or the next data element. In the case of doubly linked list, we haven't discussed doubly linked list. Yes, another pointer or to the previous node is required. So in case of doubly linked list, we need two pointers. These pointers, while crucial for the linked list to function, represents memory overhead because they consume additional memory beyond what is used for storing the actual data. On the other hand, an array which stores element in contiguous blocks of memory locations does not require this additional pointers or additional memory locations to point to the next item. The memory used in array data structure is directly proportional to the size of data it is holding, and so we can say that arrays has less memory overhead compared to a linked list. The contiguous nature or storage of element in array data structure enables us to access each element randomly using their index values. This provides constant time complexity, also known as big O of 1, which is very fast. So as I said, array data structure is good for frequent accessing of element. In case of linked list, elements in a linked list are not stored in contiguous blocks of memory. Instead, they are scattered in various locations, seemingly random memory location throughout the memory. This type of storage does not allow to access elements of the linked list randomly like array data structure, primarily because linked list elements does not possess an index value. Accessing an element in a linked list has a time complexity of big O of n. Since we cannot randomly compute the memory address of a given item in a linked list, we have to begin traversing the list from the head until we reach the desired item, or until we reach the end of the list or end of the linked list. That's why accessing elements of the linked list data structure requires more time, that requires linear time or big O of n. However, the trade-off is that while array may use less memory, they do not have the same flexibility as the linked list in terms of dynamically adding or removing elements. As always in computing, there are trade-offs, and the appropriate data structure to use depends on the specific requirement of the task at hand. Considering array data structure, arrays have their downsides too. For instance, they have fixed size. Once we define the size of the array, they cannot change the runtime. If you overestimate the size of array, you end up wasting a lot of memory. Say we estimated and allocated an array of int, say array of size 1000 equal to new int of let's say 2000. At the compile time, we estimated the size as 2000, but at the runtime, we stored only 100 items in the array. So the rest of the memory locations are unused and they are wasted. But on the other hand, if we underestimate the array size, you may run out of space and you cannot grow the size of the array. Say I defined an array of size 2000, but I end up to store 2500 elements. I cannot do that because I can only store 2000 elements in the array. Since arrays are a static data structure, they cannot grow or shrink at the runtime. We also saw how to change a static data structure, or this a static array data structure, to a dynamic array data structure. We implemented our own dynamic array data structure, and also we made it a generic dynamic array. If you haven't watched those videos, you can find them in the previous videos of this linked list. So basically, we made a static data structure dynamic by creating a new array. Say we have this array. Once we fill all the elements of the array, say I stored 7, 8, 9, 10, 11, 12. And if I want to store number 13, I cannot do that because the array is already full. What I can do is I can create a bigger array and copy all the elements of the old array to the new array, and at the last I can insert the new item. Then I have more rooms to insert more items here. The process of expanding and contracting a dynamic array to accommodate varying amount of data can be computationally expensive operations. These operations cost us a linear time, also known as order of n or big O of n, due to the need to copy all the elements to a new memory location or to new array while resizing the static array. Moreover, we saw insertion and deletion operation are not efficient with array data structure. If you want to insert or delete an element, you need to shift all the elements after it, which it takes time proportional to the size of the array, also known as big O of n or linear time complexity. On the other hand, linked lists provide a solution to these problems. Linked lists are dynamic data structures. They can grow and shrink during runtime, providing flexibility when the volume of data is unknown or changing. Insertion and deletion are efficient in linked list data structure. Adding or removing node will only involve reassigning the pointers, which can be done in constant time, giving we have the pointer to the node to be deleted. Say we want to insert an item in this location after number 7. So what we can do is we can create a new node. Say I want to insert number 11 here, so I can create a new node storing number 11 in that node. So this node is going to have a address, say 815. So what I can do is by reassigning few pointers, we can easily insert a new node at the middle of a linked list without having the need to shift the elements to the right or the left. So what I can do is, instead of storing number memory address 115 in this pointer, what I can do is I can store 815 here in this pointer 815. So this node is going to point to this node, and I will store the memory address of number 17 in the newly created node. So I can store 115 here, So this link is going to be broken and new link is created between these two nodes. So this way we can easily insert a new node at any location from a linked list by just simply reassigning few pointers. Same way, if I want to delete this node having number 7, what I can do is I can just change the pointer. Say instead of storing 900 here, this time I can store 815. So this node is going to point here. So after that I'm going to delete this node and these pointers are going to be broken. So by only assigning a pointer I could easily delete a node from a linked list. Now let's talk about when should we consider using linked list and when should we consider using array data structure. As I said, linked list offers a flexible data structure that facilitates insertion of elements at any position without needing for shifting elements or creating a new array or a new linked list and copying the elements. This avoids costly operations such as making room for new items and moving items from old array to the new array. Instead, insertion in a linked list merely involves readjusting a few pointers. As we saw, the same flexibility applies when deleting an element from a linked list. So the process of insertion, deletion, and shifting in an array can be time-consuming, often taking big O of n or linear time complexity. Also, unlike arrays that comes with an indexing system allowing easy access of elements, linked list does not use indexes. To access item in a linked list, we need to start from the head of the linked list and traverse all over to the end of the linked list until we find the item we want to access. So in this video, we have explored the linked list data structure, and I would like to summarize some key points that are crucial in understanding the concept of a linked list data structure. So while talking about linked list data structure, these key properties are crucial to remember. We said that linked list is a linear data structure. They comprise a collection of data nodes or items that are stored in non-contiguous blocks of memory. Additional memory is needed to store pointers that reference to the next node in addition to the data stored in each node. Compared to arrays, linked list allows easier insertion and deletion of elements, but the time complexity varies depending on the operation we perform. Next point, we can say accessing elements is sequential and takes linear time or a big O of n in case of linear linked list data structure. Also, binary search is not possible in linked list as we cannot easily calculate the middle element due to its non-contiguous nature. We can also say linked lists are dynamic data structure, meaning they can grow or shrink during the runtime as needed. Also, linked lists are null terminated. This signifies the end of the list as the tilde node points to null, indicating that there is no further node followed. So this indicates the null terminated node indicates the end of the linked list. This was all about linked list data structure. Thank you guys for watching, and in the next video we're going to build our own linked list data structure using a class or a struct, and we will see how we can insert or remove elements from a linked list. Please don't forget to subscribe and see you in the next video. Bye bye.